Okay, so this slide something that we have already seen, right? So this was basically an overview of this particular module, and we talked about physical vapor deposition already, and so there you have seen the conceptual system evaporation, how the film grows, the nucleation, and so on and so forth, and then sputter deposition, pulse laser deposition, and so on. Okay. So what we will do today is to start the discussion on chemical vapor deposition. Yeah. So we will again follow a similar route. So I will actually mix examples as we go along. Okay. Of different aspects of the basic principles, and also then we will follow this up with examples of how things are done. Okay. Yeah, so this is a very generic schematic of a CVD system, and you can see here several components. Yeah, and this actually does not suggest. See, these boxes does not suggest any physical shape. They can be different shapes. Okay, but shape is a very important thing because of the importance of mass flow, which would actually influence the film growth. So you have a reactor here, and you need to energize the chemical reactions, right? So you would heat it by various techniques: resistance heating, inductive heating, something called hot wire, or you can actually provide the energy by creating a plasma. So the reactants, the chemical species will be at excited states, and then you can get them to react. And plasma has other advantages where you can actually have sputtering that can be combined with chemical vapor deposition, right? And then you have electron beam can be used for exciting the reactant species. And then that can facilitate or enable the reactions. Photons, combustion. So this is, for example, if you look at historic early, people claim that some of the ancient caves, like there are so many discoveries of cave paintings dating back to 40,000 years and so on, where soot deposition is controlled by people to actually create different kinds of shapes on the walls of caves. Okay, so this is kind of a CVD process because you are burning charcoal, right, and then that produce chemicals that get deposited on the walls of your cave, but you put some mask, like maybe your hand, so the carbon or other chemicals get deposited around your hand, so you actually have masked the deposition of the carbon where you have placed your hand, so it gives you an imprint of your hands, for example, right? So there are so many things. So this is people have practiced it for a very, very long time, but as an industrial process, this is of more recent origin from the late 19th century, so that means 1850 onwards. Okay. So now, if you, of course, these days, these instruments are much more sophisticated, and you can control the thickness of the film deposited to very small values, like in nanometers, and also maybe monolayers. Yeah? So that would be less than a nanometer in a controlled fashion. So you can control many, you can repeat the dimensions, right? If you repeat the experiment, and if you are doing a batch process, all wafers would have very tightly controlled thicknesses, composition, and so on and so forth. Okay, so before the reactor, so you have a vapor, right? So you need to get the vapors into the reactor. So you create these vapors by multiple means. So your obvious thing is to use gas, right? The precursors. So what do you mean by precursor? These are the vapors, or actually the materials which will react inside the reactor to produce your thin films. So, these are really gaseous precursors, no need for any further arrangement. Take them, maybe you want to purify them, right? So, these are some things that I've kind of omitted. Many cases you may actually purify these gases. Of course, you need to control the flow of the gases. So, there will be some flow meters or mass flow controllers which can be nowadays digitally controlled. And then, or if you can have, a liquid precursor. Yeah. So, I need to convert this into vapor, okay. And you can also have a solid precursor in some cases, so we'll discuss that later on. But there are certain requirements for the vapor that goes in. So, what should be the partial pressure or vapor pressure of this material that goes into the reactor is important. So, you use a bubbler arrangement, which we have already discussed in some previous lecture, right? You have the precursor and then you use a carrier gas. So, this is typically something, it carries the vapor. Okay, so that is why it is called the carrier gas. You would not like to use a gas that would react with the precursor for this application, because then you may have some reaction inside this bottle or on the way in the tubes and so on, and something may get deposited. Okay, so usually you don't want that to happen. So, this design and what kind of gases that you use would depend on the system that you want to, you use here. For example, if I use in a fairly low temperature CVD process, let's say I want to deposit silicon oxide and the temperature is fairly low, okay. And for example, I want to grow this at 200 degrees centigrade. I'm just giving you some numbers, right? And as a crude example. So, I use a liquid which contains silicon. So, this can be some chlorosilane, right? Higher order chlorosilane, which are liquid at room temperature, and you flow this gas. So, you don't want to use oxygen, of course. Yeah. Oxygen will then react with this and then create maybe an explosion or a fire. So, you would use something like argon, helium, nitrogen, okay. If nitrogen is if you are using a resistance heating or inductive heating, okay, or a hot wire. But on the other hand, if I actually use a plasma, then what would happen? So, you will also create a nitrogen plasma. You will dissociate nitrogen molecules into nitrogen atoms, free radicals, excited states. That can react with your chlorosilane, right? And that leads to a nitride deposition. Yeah? So, you will get not pure silicon oxide. Okay. So, it is very important, the carrier gas. So, here I have written nitrogen, but you have to be very careful while using this. Okay. And if you use argon, for example, right, and I am going to use a plasma, what would happen? The plasma would ionize the argon, and that can lead to sputtering of the film as it gets deposited. So, and if that is going to be a problem for you, right, for your film, yeah, so then I may rather use helium, which is lighter, so the sputtering may be less of a problem. Okay, so we need to be careful. The conditions or the carrier gases that you are going to use would depend on the conditions of the deposition. How you energize this reaction. Very high temperature, if you go in this reaction, for example, nitrogen may actually dissociate. You don't need a plasma, right? 1200 degrees centigrade and so on and so forth. This might already start to react with many precursors, and then you may have some problem. Okay, so you have to be aware of these kind of things when you design this process. You may have an optional vacuum pump if you want to do the reaction at low pressure. Okay, so we will see this later on, what advantage a low pressure system has compared to an atmospheric pressure system. We will not discuss high pressure reactors and processes here, because that's not used in VLSI, but I already gave you one example of what? Diamond. Yeah, diamond artificial diamond can be deposited by high pressure CVD processes. And then there's something called a scrubber. Okay, meaning you can find a lot of experimental reactors that does not use any scrubber, but I would advise this to be used if you are going to use any toxic and pyrophoric gases and precursors. Yeah, and the byproducts also, if they are toxic, pyrophoric, and so on, you should neutralize them, right, before you release it to the atmosphere. Okay, very important. Okay, so some of the examples can be, if I use phosphine, let's say I want to deposit silicon which is doped with phosphorus. One method is actually I use silane, so that would go into one of these lines, and then another would be phosphine, right? Phosphine is highly toxic. Okay, parts per billion of this can be already fatal for people. Yeah, so we should not be setting up a system where you just let it to the atmosphere. Okay, very important. And then it is exhausted. It's like scrubber, right? What do you mean by scrubber? You've seen the scrubber that is used for washing dishes, right? So you want to basically remove some dirt. That's what this means. But here it's mostly a chemical thing. So you can have different designs where you have actually some absorbers which absorb this toxic gases and so on and so forth, or convert them into to non-toxic, non-pyrophoric products. Okay, so this is an LPCVD system, and here I've shown you only the reactor. LPCVD system, the major difference that you find here is that, okay, we are settling for some heating mechanism, which can be, many of the time it is resistive heating. So you have many coils wound around this, and I mentioned that we want to have uniform temperature throughout at least some part of the furnace. So it may not be just one coil, but it may be 2 or 3 zones which are independently heated. So low pressure means I need a vacuum pump, right? And then it goes out through the scrubber. And this is an atmospheric pressure CVD system, so I don't have a vacuum pump. Okay, and you can see the difference here compared to the previous slide is that you're placing wafers in a different way. Okay, so there are reasons why this is being done. We'll see that later on. Okay, now, so I'll just quickly go through this. So liquid precursors you have to vaporize and transport to the reaction chamber, and usually you have 2 kinds of vaporizer designs. So one is vaporizer with a carrier gas, something that we have seen already, or a flash vaporizer, so we'll see that quickly. So you have this vaporizer with carrier gas. You can find a little bit more elaborate arrangement, and I'm putting these slides because there are several systems of this kind in our laboratory, so you should know. Yeah. Now you can see here, this arrangement we already discussed, right? But I'm also heating these lines. Why? So I'm heating this, right? So these are heating elements, right? So I'm increasing the temperature so that the vapor pressure of the liquid, meaning this material here increases. But why do I heat these lines? Yeah, so they should not condense, right? Because if you don't maintain this temperature, you may actually, mean that can just condense, okay, and clog these lines. Yeah. So now that means a lot of work. Okay. If these lines are clogged, then you have to dismantle the whole thing and clean it up or replace the tubes and things like that. Okay. Very important thing. It can also lead to some safety related issues. So these are important components. Many a time students don't worry about this. Okay, so now vaporizer with a carrier gas. So the vapor pressure of the liquid should be sufficiently high, which means that I would not really, if it is not high, then it's very difficult to get a vapor out of it. Yeah. So what is high? So we have some typical numbers. Now, otherwise what would happen is that you have, okay, so you are passing a gas, right? What comes out would be a mixture of the vapor of this liquid and the carrier gas. Okay? So the partial pressure of the reactant vapor in that gas mixture would be small. It would be mostly just, let's say, if I use argon, only argon, right? So otherwise, meaning I should have sufficiently high vapor pressure for this. Yeah, its goal is just to transport this into the reactor. So you can ask, for example, why should I use a carrier gas in the first place? I just heat the whole thing, right? I get a vapor. So then it would be maybe difficult for me to, so it's 100% the vapor of this. Okay. But I'm using a carrier gas, it actually can carry, meaning increase the vapor pressure by, meaning even at low temperature, I can get sufficiently high vapor pressure. So that's one thing. And the other thing is that I also have a mechanism to dilute it. Otherwise, it's going to be 100% of the vapor of this. Okay. Yeah. So this is the carrier gas does two roles. So it actually gives me higher vaporization of this, right? And also I get a possibility to dilute the vapor that goes in. And dilution means I don't really want to have any reaction between the carrier gas and the vapor. Now, vapor pressure of a given liquid can be controlled by setting the temperature. So you heat it up, usually the vapor pressure goes up. Okay. So you can see that it's just that I need to, if I don't have sufficient vapor pressure at room temperature, then I need to increase the heating. Yeah? I need to heat it to high temperature. So I would not really look at this process if I need to have a very elaborate arrangement to actually heat up the whole flask to very, very high temperatures. So this is something that you may actually have seen. This is the phase diagram. So you have this solid phase. So you are actually, this is a solid. You increase the temperatures. At some point, it will start to melt. Okay, and of course that depends on the pressure. So if the pressure increases, then you need to heat it to higher temperature. This is a generic thing, right? And then at some point, the liquid actually would become gas, right? High temperature, this is going to gasify. And then there are some details like you have a triple line where you have this equilibrium between all the three phases, solid, liquid, and the gas. And if you take at a specific volume, take one particular volume value, this is, you can then reduce this to a two-dimensional plot. So as you increase the temperature, right, this is a solid and it becomes a vapor, okay? Yeah. And then it will start to melt at some point. And you have also vaporization of the solid depending on the pressure. And this is called the triple point where you have all the three, right? And then you have what is called a critical point where you cannot distinguish between the liquid and the gas. So this is beyond this point, it's called a supercritical fluid. What we are interested in is actually I can increase the temperature and then get a vapor, more and more vapor into this. So you can see the vapor pressure would increase, right? The pressure of the vapor would increase. So this is one thing for dichlorosilane, which is actually used for deposition of silicon. You can use it for epitaxial growth of silicon, deposit amorphous silicon. You can use it for depositing polycrystalline silicon, and so on and so forth. So at 300 Kelvin, you get already 2 bars. That's the pressure, vapor pressure, right? Or 1500 torr. So typical vapor pressure you are looking for any of these precursors at room temperature is about 7 to 8 bars. Okay. So this means, as an example, dichlorosilane is a very good precursor, right? Even though it is a liquid at room temperature. So it has fairly high vapor pressure, so it's very easy to use in a bubbler. This is taken from this company's data sheets. So Air Liquide actually makes many of these products used in semiconductor processing. Now, so this is also very important thing, because as you increase the temperature, what is going to happen? Increase the temperature, the pressure increases, right? Vapor pressure increases. So you would have higher evaporation, right? The evaporation rate increases, which means that the amount of this precursor delivered to your reaction chamber would actually increase. And this can have a significant impact on the growth rate, okay? So this also means that if I want a repeatable growth, I should actually control the temperature very precisely. Yeah, I'll give you an example. So we are actually doing here phosphorus oxychloride, a bubbler arrangement, something similar to what you have seen, for phosphorus doping of silicon for making PN junctions, yeah, for making solar cells. So you have seen the solar cells that we make, right? I showed you the solar cells, right? One of the previous lectures, introductory lectures, I showed you the solar cells. So we use phosphorus oxychloride, which is a liquid at room temperature, and then you bubble nitrogen through this. Okay. And we were having, initial stages, a lot of trouble, because every time we do this process, the sheet resistance of the emitter diffusion would actually be different. It was very difficult. We were not getting controlled sheet resistance. And the assumption there was that, okay, the clean room where this whole thing is placed has fairly well controlled temperature. Okay. That assumption was not correct. So we had to then buy a temperature controller, so which actually has some a special type of cabinet in which you place this the container of this POCl3. Because of safety issues, it comes with a lot of valves and so on and so forth. So you need to have this specially designed heaters, heater cabinets to house this. So it's also not very cheap. Actually, we have to pay some 8 lakh rupees for this the heater cabinet for this purpose. Okay, so this is a very important thing if you are doing any CVD process, and especially in academic environment, not necessarily well taken care of. So if I use a vaporizer, though I cannot just say, okay, this is the vapor pressure at this temperature, so I use that value to calculate what is going to be the amount. So pressure, if you actually, if you know the pressure of this, or partial pressure of a vapor in a chamber, I can find out what is the density of these molecules by using PV is equal to nRT. Yeah? I know the volume, I know the temperature, so I can find out how many molecules are there per unit volume, or from that equation. So here what you find is a simple equation that actually relates the vapor pressure of the vapor in the bubbler, okay, and P0 is the vapor pressure when there is no carrier gas. So you turn off the carrier gas. So you have, what is vapor pressure? You actually have this carrier, meaning the bubbler, okay, and you have it at a certain temperature, yeah, and it's completely closed. So what would happen now? It's not at the boiling point, okay. So what would happen if it is a closed container and you are heating you are maintaining the temperature, okay, of this at some value, okay. So will there be any vapor in the container? If there is, if it is not filled with the liquid, there will be something, right? Some vapor will be there, and will the amount of vapor increase with time? To come to some equilibrium value, because what is happening there? Some vaporization would happen, but also at equilibrium there will be also condensation. Okay, as a consequence, you would have after some point, right, will come to a steady state, right, where the vaporization rate and the condensation rate would equalize, and you would have a vapor at a certain pressure. So that is actually the P0 that we are talking about. There is no carrier gas, okay, and that's something that we can find from the pressure versus vapor pressure versus temperature graph. Okay, but then as you increase, meaning you have a bubbler, so you're passing this carrier gas, so then the pressure is going to change, because now molecules of this carrier gas is also going to come there. So that would modify the pressure, and this is the equation. And specific volume is actually just the inverse of density in this case. So you can substitute it and find out what is the pressure of the vapor in the bubbler, and that would be also the pressure at which it will be delivered to your reactor. So this is the other way that you have a flash vaporizer. What you have is actually a flask which is heated, okay, and you are actually delivering a liquid into this using a pump which can actually control the flow very precisely. So peristaltic pump, where you can actually find out yourself what is the construction and so on. But it's good to just know that this is a type of pump which is very, very precise. Flows can be maintained. So just the liquid falls here, and then it's a flash evaporation, right? So it's like, you take a pot, a steel pot, and then you heat it with no liquid, and then you're pouring a little bit of water on it, right? So this is something like this, flash evaporator. Okay. Heated line is used again. Why? You don't want any condensation. Yeah, it goes to the reactor. So very simple, right? Solid sources, what do we do? So this is a difficult process. So solids that are easily evaporated may be used in an arrangement similar to what we have seen here, right? So you heat up the solid, and then it evaporate at reasonable temperatures, not going to very high temperature. And an example in case is tungsten, and if you heat it to 2000 degrees centigrade, this is going to be your vapor pressure, right? Compare this with what we are talking about, right? We want a vapor pressure of 7 torrs at room temperature. Yeah? So this is, tungsten is one of the material with one of the, or element with one of the highest melting point, right? So what you do in such cases to react them with appropriate gases, that will give you gaseous products, and that is then carried to the reactor. So you can see this tungsten, you react with chlorine, you get tungsten hexachloride, and this can be done at 800 degrees centigrade. So this is somebody had used this kind of system where you have tungsten chips, and then you have chlorine going in and hydrogen to dilute it. So you have gaseous vapor of tungsten hexachloride. These days nobody does this kind of stuff because you can buy, tungsten hexachloride off the shelf, yeah? Or hexafluoride can be purchased off the shelf. By the way, this is important because tungsten is used as a plug material in VLSI. Okay, for after you make the contact, you use it as a plug. Okay, tungsten plug technology is very important. Okay, now different types of reactors. So you'll find some reactors most of these APCVD reactors have some kind of construction like this. You have a furnace, and you place your carrier on which you're going to place your vapor, that's right, and the vapors are placed on the carrier, like this. They'll be lying on the carrier side. So important thing is that now if you look at the precursors are flowing in, okay, as they proceed, they actually see a smaller cross section. Okay, so there is a reason why that is being done. And in this case, you have a carrier, okay, and then you place if these are silicon wafers, for example, they will keep these wafers like this, vertically. So this is a better packing arrangement, right? I can load a large number of wafers compared to this. So let's say I have 8-inch wafers, right? 8-inch diameters. So in an 8-inch length of this, I can just use one wafer, right? But in this case, 8-inch length, if the diameter of this furnace is large enough, okay, and then I can actually keep many wafers. Yeah. So in this case, of course, the diameter of the wafer is 8-inch. So I need to also have this thing also more than 8-inch, right? Yeah. So here you get, you can actually process larger number of wafers in one shot. Okay. But then why people use APCVD? So there are certain advantages. You can actually have very good deposition at high temperatures. So epitaxial reactors are typically designed like this. So we'll see this later on, especially when you want to grow thick films, yeah, of epitaxial silicon. LPCVD, this is something, some companies use RPCVD, reduced pressure, so the same as LPCVD. They want to make a distinction, right? Yeah. What is their selling point? Unique selling point is replace L with R. Okay, so the problem here is you are actually heating this reactor. The whole thing is being heated. So the wafers will be at some temperature, and more or less the same temperature would be there at the walls. So whatever gets deposited on the wafers and the boat and the furnace walls also. Okay. So typically this kind of furnaces are made using quartz and the silicon dioxide, right? And let's say I'm going to deposit silicon nitride. So as the thickness increases, these are two materials, and the film that is already deposited is seeing, let's say, 800 degrees for 4 hours today, and so on and so forth for 3 years, right? So for a very long time, it was at 800 degrees centigrade. So it would have started to crystallize, and there will be mismatch between the deposited material because it's no more amorphous, right? And then there will be huge stress. So flakes of silicon nitride would start to fall off from the furnace. So I need to then do cleaning of this tubes quite often. So that is not going to be an easy task. I'll have to take this out, right? Or I may actually, what is being done these days is that you actually pass through this some gas that would etch the deposited material. So this also means that contamination is not necessarily of the electronic type. It can be just particles of the flakes, yeah, this different materials, and that is not necessarily a good thing for. In fact, that is not good for any VLSI processing, because you want a continuous smooth thin film, but if you have flakes falling on the wafer, that's not good. So this is also, I mentioned about cleaning this chamber. It's not an easy task because these are going to be big things. So if you take a furnace tube, this may be so long, right? And typical process is to take this and then put it in an HF solution, hydrofluoric acid solution. So HF will of course etch the quartz also, but that's fairly thick, right? The quartz wall of the furnace is fairly thick, and then what is inside actually, what you have deposited will not be so thick, so I can etch it. So I'll keep it for a couple of days and then take this out. But hydrofluoric acid is fairly dangerous, so we have to be very careful. You can't keep this in a glass container, right? Because it will etch the glass. Slowly your bottle is no more there. Okay? So you need some plastic, Teflon. These are horizontal furnaces. So I think I'll show you at some point some short videos showing this things will be there. Or you can actually if anybody is interested, we can organize tours of the labs with the TAs, okay, where they can explain you, okay, this is the furnace that you've seen there, yeah, was explained in the lab. So most of the tools that we discuss in this course are there in our labs. So this I already mentioned, you have multiple zones. If you have a horizontal furnace these days, you also make this vertical. The construction of this is similar. Only thing is you save real estate. Real estate is expensive, right? So you actually have this furnaces mounted like this, vertical. That is also possible. Of course, then you need to do something against gravity. So, right? So you need to actually control everything from this. The flow is going to actually change, yeah, and so on and so forth. Then there will be problems with convection. So all these things have to be then taken into account. Why do you have multiple zones? So here from these ends the heat loss will be higher, right? So you would have a drop in the temperature. So usually if I just have one zone where all the elements are given the same amount of energy, right? Same current flows through all this single winding. So then I would get a very short, what is called a flat zone, where the temperature is almost constant. But you want all the wafers to see the same temperature, so you keep this three zones, meaning one example, right? So you heat this would actually get higher power to compensate for the losses, yeah? That also happens here at this end. So usually use PID controllers for controlling temperature, and the PID values have to be set differently for the three zones. Okay, so here usually cold gas is coming in, right? So and here hot gas is going out, right? So then you have a problem. I can't have, this figure kind of suggests you that these two zones are nearly identical. That is not the case. So this you can see here, right? This is the inlet. It goes into this. So this is real data from our laboratory. Okay, so this is another type of thermal reactor where you have a single wafer that is being processed, and you have what is called a shower head. So the gases or vapors come through this. Shower head is actually used to ensure uniform flow of the vapor onto the vapor surface. And you have a susceptor. You can heat it by using lamps. Okay, so if you use lamps, then it becomes possible for you to rapidly heat the wafers. Okay, so this can be used for what is called rapid thermal CVD processes. It's it becomes important when you want to deposit ultra thin layers of materials. So you don't actually spend much time heating up a furnace and cooling it down and all this. Right? You have seen that in the case of oxidation. Okay, rapid thermal process, what it meant. Okay, now there are certain advantages. You are actually heating, targeted heating of the wafers. So no deposition on the chamber walls. So in this case, so less particle contamination and so on. So these are some other reactor designs. So this is really barrel reactor. So it's like a barrel, right? And keep the wafers on the sides of this barrel, and sometimes it is rotated, okay, for uniform deposition, and then there is something as an insert to control the gas flow, and this is called a pancake. So something like a pancake, right? And you have a gas coming in, and there's some flow like this. So these are mostly used for epitaxial growth of silicon, and very important thing you may actually identify here is, again here the gas is flowing in, right? And then the cross section available for the gas to flow decreases as it proceeds. Okay, a very important thing, because the gas flow is very important in the CVD case. So we had seen in the case of oxidation, we had two things controlling the growth of the oxide. What were these? Do you remember? We discussed about three kinds of fluxes in the furnace. So the flux of the reactant gases onto the wafer surface, right? So that is the first one. Yeah, from the flowing gas. The second was, through the already grown oxide layer, there is diffusion, right? And then the third one, there is a reaction at the interface between, meaning at the surface of the silicon. Okay, so three fluxes. And when we did the analysis of the oxide growth, Deal-Grove model, when we developed it, we actually ignored or said that one of them is not important. Which one was that? First one. Yeah? We said first one is not important. Okay. But now you can see here, in the oxide growth case, we discussed about three fluxes. Are all the three present here in a CVD deposition? So what he's saying is that there is no diffusion through the already deposited film, because you are depositing on top. Okay, so you have something deposited, you are not going to actually have a deposition at the interface. It is going to deposit on top. So there is no need for the reactants to diffuse through the already grown layer. Okay, so the second flux is missing, meaning that's not important. That process does not happen, or not important for this CVD reaction. So then you have two fluxes. One is actually how the reactants are transported to the surface, okay, and then what is the reaction rate on the surface. Okay, so then the flow of this reactants become very important. So this is a slide you have already seen. So you have flow through a tube, and then you can have turbulent flow, which can lead to non-uniform film growth, and especially in this case where the flux of the reactants through the gas is actually the gas medium is very important. Okay, and in the previous case we ignored it, but of course under certain conditions that this is actually a laminar flow. So you can see here also you would really like to maintain a laminar flow, and that is defined by Reynolds number, which is defined by this equation, and all these parameters are defined here. Okay, so these are conditions for laminar and turbulent flow. Now another thing very important for see this, I repeat this many times, that when students do the processes in the lab, right, repeating the experiment is a challenge many a time. Okay, and that is because you have actually read the textbook and said that the position depends on the temperature and the pressure, and then I go and look at the temperature reading on the furnace and it shows 1000 degrees centigrade. I look at the the pressure indication and it shows me some pressure. Okay, so I have, but that's not what is happening inside the chamber, right? So so you need to be a little bit more, try to understand a little bit more of what is going on inside. Okay, so these are what are called dead zones. Okay, essentially you have a gas flowing in and it spreads like this. So basically it just does not hit these areas. Yeah, it's like this, that you have a big room and small window, right? And there's heavy wind. And how do you escape from the wind? Go to a corner of the room, stand there. You can see the wind passing by, right? Yeah, same thing here. Yeah. So this is then a dead zone. It's called a dead zone. So there's no, of course there will be some diffusion and so on and so forth, but you are not interested in that. Okay. So controlled depositions are not possible. So you need to actually keep your wafers where there is a laminar flow of the gas, okay, and where the temperature is uniform. Yeah. So you place the wafer at exactly the same position every time you do the process. So here you can have, it's a dead zone, so there is no movement of particles. You have a class now? Okay, so you have this. So you create particulate problems. So basically, you can have all the reactant gases accumulating here and create. Okay, so now the chemical reaction rate is decided by two things. Reactants should collide with each other for a chemical reaction to occur. So that is very important. So higher the concentration of the reactants, right? Higher the probability of collision. So that would influence your reaction rate. So that is what we were discussing about the bubbler. If you don't use a carrier gas, for example, right? So you can have high reaction rate. Chemical reactions are thermally activated, so temperature plays a very important role.